Example. Find the solution that satisfies the integrodifferential equation. And the following initial conditions. Solution. In this example, we will use the Laplace and inverse Laplace transform to find the solution. First, take the Laplace transform of both sides of the equation to convert the integrodifferential equation into an algebraic equation in terms of a new variable s. Apply a Laplace transform of derivatives, integrals, and a constant. And then, substitute the given initial conditions. Factor out a common factor. Combine these terms into a single rational expression. And divide out a common factor between the two sides of the equation. And then divide both sides of the equation by this polynomial. And then, factor the denominator. Now we have the Laplace transform of the solution. In order to convert the solution back to its original variable t, we have to rewrite the rational expressions such that their inverse Laplace transforms are easy to find. Instead of using partial fraction decomposition to rewrite it as a sum of two simpler rational expressions, consider it as a product of two simpler rational expressions. Because we have a product of two Laplace transforms, its inverse Laplace transform is the convolution of their individual inverse Laplace transform. Afterwards, take the inverse Laplace transform of the whole equation to convert it back in terms of the original variable t. Rewrite each term such that an inverse Laplace transform is easy to see. Recall the convolution property of Laplace transforms. And then, apply the necessary inverse Laplace transforms. Next, write the convolution as an integral. Rewrite the exponential factor, so that the integrand can be simplified. Because this exponential factor does not depend on the variable of integration, it can be moved outside the integral. Instead of using integration by parts, substitute the exponential function equivalent of the hyperbolic function. Factor out the constant, combine the exponential factors by multiplication, and simplify using a property of exponents. And then, proceed with integration using just an exponential function rule. Evaluate the definite integral using the fundamental theorem of calculus. Simplify and factor out a common factor. Therefore, The following function represents the particular solution of the integrodifferential equation under the required initial conditions. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.